All right. So this video is going to be going over the front suspension design for the trophy truck. So that includes the steering, which this ended up being a lot more complicated than I thought because I ended up rebuilding it from scratch. I was originally intending on copying over a lot of the components from the previous Ultra 4 design, but I found some room for improvement, which I'll get into in the video as far as tie rod placement. And then I also moved to a traditional rack and pinion design with a hydraulic steering pump. So I think this is a lot more robust design and ended up taking quite a bit more time. We're also going to get into the lower control arm design, which is using a mixture of billet aluminum and billet machined steel. And then also the upper control arm trophy truck J arm, which I'm not 100% happy with this yet, but as a placeholder, it works to get all the suspension to cycle properly. And we also have the coil carrier and bypass shock, as well as the bump stop with the slapper arm in there as well. So we'll be going over that part of the design as well. And a couple things have changed on this design since the last time we saw it. I modified the sway bar arm because the angles at compression and the angles at ride height were a little bit too severe. So this is what it looks like now. To my eye, this still doesn't look right. It looks like it's just way too big, but this is the best that I could come up with to accommodate all of the suspension droop on this, because if you remember in the rear, it's got 50 inches of travel in the back. And so these arms are just incredibly long as a result of that. The other thing that I did in the drivetrain is I swapped out the engine. I had originally imported a supercharged LS base engine for this, and I've since swapped it out to a GM Performance 632 big block. This is a model that I found on Turbo Squid. I don't love it. It's very low poly and it has it's a really heavy file and it has a lot of extra details in the wrong places. And also when I imported it, the units were wrong completely. So I had to do a scaling operation, which took absolutely forever, but here it is. I was surprised that it wasn't as good as I was expecting, because this is a licensed file, licensed by GM through Turbo Squid, but it's just a bad model. But anyway, I cleaned it up as much as I could, added some colors on it, and I'm not confident that it is the exact size that it needs to be as a mock-up, but it's pretty darn close. And it still looks pretty cool, despite being low poly. You can see all those lines in there. And then the last thing I did on the drivetrain is I swapped out the 4L60E, which according to everyone's comments is made out of cheese. And so I swapped this out for a Turbo 400. This is a really great model that I found on GrabCAD of a Turbo 400. And these are usually a pretty consistent envelope size. And then the internals would be all race custom machined gears, billet everything, and it looks really great. So let's jump into the time lapse and we'll go over the front suspension design for this all-wheel drive trophy truck. Okay, so the first thing I'm going to be working on is the steering, and that starts with the steering tie rod. So I have two big rod ends that are going to be tying the steering rack to the portal hub, and I just need to make a simple boss feature to represent the tie rod tube and import a weld nut from McMaster into the steering tie rod. So if you remember on the previous design, the steering tie rods were made out of billet, and that worked out really well for that design because it allowed me to put some really cool stylistic elements in that part of the design. But for this design, the sort of design motif is to keep 4130 chromoly in as many places as possible instead of billet. So a traditional chromoly tube here will work just fine for the steering tie rod. And what I wanted to do was copy over a lot of the components from the previous Ultra 4 steering assembly, but I ended up redesigning it almost entirely. That previous design had just a piston and a mounting bracket that was constrained in all three axes, so it was plenty strong, but it was a direct hydraulic steering system like the ones that rock crawlers use. So it's not going to be super fast. What I ended up realizing on this design was that a traditional rack and pinion was the way to go, because those allow you the opportunity to move the steering a lot faster with hydraulic assist rather than hydraulic direct steering. And for the lower control arm, I'm taking inspiration from Mason Motorsports, who just put out a lower control arm that has a machined steel component in the center and then two billet aluminum pieces on the outside. And so the load bearing component is the machined steel 4340 material, and that interfaces with the spherical bearing and takes the majority of the load on the lower control arm. It's also the point where you need to have some thin wall thicknesses to have clearance for the hub as it cycles through steering. And what I learned on the previous Ultra 4 design, when I ran that lower control arm through finite element analysis, there was a weak part right here. And so replacing that billet aluminum with billet steel made a ton of sense. And it also makes the part look incredibly cool. So rather than one big giant piece of billet, it's going to be 3 pieces clamped together. And rather than wishbone shape or a regular A-arm shape, this is going to be an offset A-arm, sort of like a J-arm, but not quite. And so I just need to make the basic shape of this lower control arm here and capture all my dimensions for the offsets of where the bushings are going to go versus where the spherical bearing is going to go, and drop that piece in and see how it looks. And so whenever I'm doing design work on a part that I know is going to end up looking way more complicated, I just like to start with really simple blocky shapes, because I'm imagining just a big chunk of machine stock billet and then carving the piece out of that. And the simpler the features are to begin with, the easier the time you have iterating on it. Like on this part, I ended up changing it from a flat shape to sort of a V shape. It has a little angle in the bottom of it in the final version. But because I didn't design this all the way through the DFM, design for machine process, from the beginning, it was really easy to edit this part without redoing a ton of work. The other advantage there is if a part starts to look really pretty and really cool, there's a little bit of a mind game that goes on where you're disincentivized to edit it or make a completely new revision of it because it already looks so done and so pretty. Whereas if you need to iterate on a part, having really simple features to edit makes that process go a lot quicker. So now I have the steering tie rod and the lower control arm in, and I can start thinking about where all the steering components need to be. And one huge opportunity that I saw on this one was that if I drop that steering tie rod a couple of inches down to the center line of the wheel, I gain a ton of clearance for steering angle. On the previous Ultra 4 design, I only had plus or minus 20 degrees of steering angle, which was not enough. On this one, the target is plus or minus 30 degrees of steering angle. And you can see that tie rod is nested up off of the center of the wheel. And so if I drop that down to the center of the wheel, I gain many inches of clearance. So what that means is I need to modify the portal hub tall knuckle design to have different pickup points for the steering tie rod. So now I can open this up and start deleting stuff that I don't need, deleting all the mates that were positioning that spherical bearing, and delete all those pocket cutouts. And I also ended up rotating that spherical bearing. I don't know if this is more or less strong than the previous design. I don't think it matters, but it made the machining features a lot simpler, because if you remember on the last design, I had this weird clamp that was going around and hugging the spherical bearing and tying it to the portal hub. Whereas this one, I can just have 2 regular bosses that stick out to grab it. We'll go over that. So now I can move that spherical bearing into place, start thinking about what features I need to capture it. The only issue with doing this on the design is that it makes the mounting hardware interfere with the steering tie rod. Mounting hardware interferes with the lower control arm mounting hardware. So I needed to have a little bit of an offset, but I ended up with very minimal bump steer. And I'm making that bump steer compromise for the sake of more steering angle. So now I can open up this portal hub tall knuckle, start deleting the features that I don't need. This part was kind of tricky because a lot of these features were referenced to each other. So if you delete one, it deletes like 20 other subsequent features, which was not ideal, but I had to chase those down and make sure I have everything independent and not referenced off of each other. And it ended up being okay. So this part is so complicated. I mean, that design tree has hundreds and hundreds of features. And anytime I make a modification to this part, it ends up being quite a lengthy process to chase down any rebuild errors or any weird features that might have ended up being modified. Like for example, here, this pocket cutout was tied to the height of the tall knuckle, which I ended up reducing on this design. And so all the reference sketches in there were sort of broken. And so I had to fix that, make sure all my fillets were right, make sure all the features were actually machinable, and make sure it looked the way that it's supposed to. But yeah, on a part like this, I would never have designed something like this even 10 years ago. When I got started in the machining world and the engineering world, all we had was 3-axis CNCs. Maybe you would see a 4-axis, but it was like a really custom modified machine. But now they have these 5-axis mills and these really precise ball end mill operations that you can run. So you can basically make the part look like whatever you want. And it's going to take a lot of machining time, but it is possible, whereas that wasn't always the case. Design for machining was a really intensive process, and there would be a lot of back and forth between the machinist, programmer, and the engineer to make sure that features were actually machinable. And if you got a part that was all wonky with weird features that were not machinable, you could tell immediately that the engineer didn't know what they were doing, or they had never set foot in a machine shop. So it was a huge advantage I had when I was young, growing up in a machine shop, carrying that into engineering and knowing exactly what is and is not possible. That being said, these days, almost anything is possible with these 5-axis machines. They can make some really wild curves and organic shapes. And especially if you bring additive manufacturing into the mix, like 3D printed metal is becoming stronger and more common. You can make almost anything that you can think of. And that's especially exciting for the world of generative design, where you use an AI tool, not like ChatGPT, where it's text generation, but mechanical design generation, where you can optimize a part in FEA to add material where you need strength and remove material where you don't need it. Really optimize stuff to make it as strong as possible, as light as possible, and also be manufacturable. So these are those two little ears that are sticking out. They're going to capture the hardware for the spherical bearings for the steering. And I really love this design way more than the previous one. It's way simpler. It makes the part all one rather than having a secondary component to capture those. And it ended up looking really good, really strong, and tons of clearance. So I just need to add a little lofted cut here. So that's an angled cut. It sort of takes a cone shape in the part, and that adds clearance for the cylinder that represents the tie rod as it angles in and out. So now I'm just grabbing some hardware from the previous design to see what kind of an offset I need on that front rod end for the steering tie rod. And it's sort of hard to tell while this is moving fast, but the steering tie rod is not parallel to the front of the vehicle. It's at a very slight angle with like maybe an inch or so offset, which will contribute to a small amount of bump steer, but I needed that clearance between the nuts and bolts to be able to drop that tie rod down to the center of the wheel to get more steering angle. So again, this is another compromise that I chose to make, where we're sacrificing the specification of increased bump steer for the sake of the specification of increased steering angle. And I think that was the right choice to make. So now I can just drop that nut in, and I'm leaving a 1/4 inch gap between those two pieces of hardware. And although these components will be cycling up and down really, really fast, there's zero chance that they're going to run into each other, because the steering is going to be tied into the bulkhead and constrained longitudinally. So nothing should move in that direction. So it is kind of scary to have two parts close to each other that are cycling. But just like my grandfather always said, when you're moving stuff, an inch is as good as a mile. So in order to figure out how much clearance I need on that upper control arm, I'm drawing a sketch in here that represents the wheels as they cycle their steering plus or minus 30 degrees. And I need to make some serious mods to that lower control arm to get the right clearance for the steering. So I got kind of stuck when it came to the steering box design. I looked at a ton of references online for trophy truck steering boxes, and what I ended up realizing is that almost everybody uses a rack and pinion design. And it seems to me that the main advantage to that is faster steering. In a regular build, this would be a component that you just buy off the shelf, like the whole steering assembly. They're not that expensive. They're really well engineered, and they would work for most applications. But for this one, as a design exercise, I wanted to build one from scratch so that I could understand how it works. And that's usually the best way for me to do that. So I look at an example design, figure out what components are there, and then try to make my own version of that optimized for the use case. So since everything on this design is scaled up, because we're using the 58-inch Mickey Thompson tires, I needed to make a custom rack and pinion steering box. And that part of the design is not done, but it's at least a placeholder in there that I can come back to once I have a better understanding of exactly what components are needed to make this work. But it seems to me the basic components are: you need to capture a hydraulic steering pump, you need to capture a pinion gear, and you need to capture a rack gear. And from all the pictures that I saw online, it looks like all that stuff's made out of steel as well. So again, another departure from billet 7075 on this design in place of steel for strength and rigidity. So the next thing I thought I would do is make a rack gear design with teeth, but I ended up finding that McMaster already has a ton of these, so I just picked the biggest one that they had. And so this part of the design didn't end up getting used. I just ended up pulling one from McMaster. So after sleeping on this for a night, I thought about the fact that rack and pinion gear designs are pretty standardized. So I looked on McMaster to see what they had, and they had one that was the perfect size. It had really big teeth, it was the right length, and it came with the rack gear and the pinion gear. So I know they're going to mesh up perfectly. That way, I don't have to think about gear tooth design or spacing or strength or anything like that. I can just pull something that already exists. I remember one time an engineer told me, this is a really high level guy, like a tech startup founder level guy. He told me one of the principles that he follows is never build anything that you can buy, because somebody's already done the work for you. And the development time that it would take to build something from scratch that already exists is time wasted. So I'm just pulling these gears from McMaster, and I know that they're going to be better than anything I could come up with at a first pass. And the other cool thing about this is I get to try a new type of mechanical mate in SolidWorks that I've never used before. I've used their standard mates and their advanced mates, but they actually have a rack and pinion mate built into SolidWorks. So you can put two gears in and they actually work. You can move them in the assembly with relation to each other, which is what you're seeing now. And I just think that is so cool. It just makes it feel like a real mechanism rather than a model. So now I have the rack, the pinion gear, and the hydraulic pump, and I just need to figure out how to capture all these components in a housing. So what I'm going to do is have a slider box for the rack gear, and then a housing for the pinion gear, and then these two machined end caps that attach the hydraulic piston to the rack gear, again out of steel. And this is completely based off of a reference design that I found online from off-the-shelf trophy truck steering racks. So I know this is the right configuration of components to make everything work in a way that's strong and tested, but just like everything else on this design, scaled up by about a factor of 1.5. And then I'm counting on the fact that once I have that rack gear, I can put that in a machine and cut in the features that I need, like the bolt holes to capture it. And because this rack gear is longer than I needed it to be, I can utilize that space on the end for bolts without worrying about needing those extra teeth down at the very tips of the gear. So now I just need to make a mounting plate for the hydraulic cylinder that's going to grab it, hold it in place with a clamp so that it's easy to assemble and disassemble. And it's going to be constrained laterally against the movement of the piston while the steering is articulating. So this is just going to be a simple C-clamp for this. And then I'm going to capture it on top with some bolts. And so this holds the part up vertically, constrains it laterally, and has lots of meat for the clamp to attach to. So then I just need to make a circle, chop it in half, and then extrude it out to make the clamp for the top. And then adding another plane on top so I can add those bolt holes. And I'm using 1/4-20 hardware on here, which I think should be fine. 1/4-20's stronger than it looks. So now I just need to make some stylized pocket cutouts for this part. There's no structural benefit to this. I just wanted to be able to see the PSC hydraulic steering pump logo through the clamp. That's the only reason I did this, which is kind of a silly reason, but it also makes the part look cool, which is sort of the point for a design exercise like this. And not that complicated to machine. There's that clamp, and now this assembly's looking great. So now I need to figure out how to house the slider for the rack gear and the housing for the pinion gear. And I didn't get very far on this. I sort of got stuck because couldn't figure out where the bearings needed to go. So I just made a part sort of as a placeholder, and that's what we're going to be working on here. So the first is just a simple circle to capture the pinion gear, and then a big boss for the rack to slide through. Thing that I don't know is whether these slide with grease or whether they slide with Delrin bushings. That's something that I need to figure out. I also don't know how to capture the bearings for the pinion gear, and I don't know where the steering input is going to be yet. So this part is sort of a boxy envelope placeholder for the time being, and then we'll revisit this design later on. to finish it up. But I ended up abandoning this housing for the time being because the goal for this part of the design series was to finish the steering and the front suspension. And I didn't want the steering to take too long since I already had to rebuild it from scratch. And as it stands right now, this mechanism is good enough for the steering to cycle in the assembly and the suspension to cycle as well. So that's fine for now. Once I do the bulkhead, then I'll revisit the steering. So the other thing I realized was the steering input was going to crash into the differential housing. So I needed to flip this whole assembly upside down, which ended up making the whole thing a lot simpler because it allows an opportunity for the mounting brackets between the steering rack and the steering tie rods to be just plate steel rather than a big complicated billet bracket. So I'm just going to take these two end caps that tie the steering piston to the rack and then add some more mounting features for sheet metal. So luckily for me, the width of that rack gear was almost exactly what I needed to capture the rod ends. So the sheet metal mounting bracket can be flat rather than having any bends in them, which is going to make it a lot easier to fabricate. And this is going to be a really simple shape. It's just 2 lines offset and 4 holes offset with some clearance. And on the previous Ultra 4 design, this was one gigantic piece of billet, and I didn't love the way that it looked or functioned. So I'm excited to be making this one out of simpler sheet metal, but it was a little tricky to get all the clearances in the right place so that the steering tie rods don't crash into the sheet metal at full compression. So what I'm doing is I'm making half of the design in sketches, and then I'm just going to mirror that over to the other side. That way I don't have to have a ton of references. But this ended up biting me in the end because every time I iterated on this design, the mirror would break. So I don't think I'm going to follow that design process again. I think just making one big sketch without any mirrors in it is the right way to go. That way, if you modify one thing, you modify everything. And so this is just 2 flat pieces of sheet steel with some internal gussets, and it should be really easy to fabricate, and it should be plenty rigid in the axis that it needs to be. And then the whole thing's just mounted up with a few bolts, and we have a steering rack. So the next thing that I need to start thinking about is shock mounting location. Ideally, you want the shock to be as close to that pivot point at the end as possible. But since I have those big giant tall knuckles in the way, I could only mount the shocks about halfway up, which I think is fine because on this design, I've got 30 degrees of up travel, 25 degrees of droop. And so that gave me 30 inches of wheel travel on the front, which is pretty nuts. I mean, a lot of trophy trucks have 30 inches of wheel travel in the rear, but this is just as big as possible. And the way that I achieved that was I put those mounting points on the inboard side as close as possible to each other. And then I increased the width of the vehicle a little bit so that I could get the maximum lever arm angle on those trailing arms. And so what I need to do next on the lower control arm is figure out how to attach those 3 pieces in the assembly together. So if you remember, I have that machined steel piece in the middle and then 2 billet aluminum pieces on the outside, and they're going to be sandwiched together. So what I'm going to do is bolt them together and then pin them together as well. And the bolt just ties the assembly together longitudinally with respect to the direction of travel of the vehicle. The pins take the main load bearing force between the part that's connected to the wheel and the parts that's connected to the vehicle. The reason you want to do that is because bolts are only strong in one direction in their long axis, whereas pins are stronger in shear quite significantly. So anytime you have a shear force between 2 components in an assembly, you want to pin them together. The other main thing is pins are really good at locating features together. You can precisely cut a pin hole using a machine tool called a reamer, whereas most clearance holes for bolts are just cut with drills, and drills are not very precise because they wobble. So you drill a pilot hole with a bolt, then you drill a pinhole with a reamer, and you can really place that hole accurately so that the 3 components in the assembly are tied together in a really strong way. So the next thing I'm doing is making some pocket cutouts for the shock mounts, and I'm just copying similar features over from the previous A-arm design so that I have clearance for the hardware and the spherical bearings and lots of room for the actual shocks to pivot in and out of that assembly. But on the previous design, the shocks were straddling on either side of the axle. But on this design, I want the shocks to be on both of them on one side of the axle. So the coil carrier and the bypass shock are both on the same side. The only way to do that was to tie them together using one really, really long bolt. And I don't think that's the strongest way to do that. So I ended up modifying this design, but it's still worth walking through the exercise of how I did this. So I'm putting a pocket cutout on the back for a lock nut, and then I'm going to have one really, really long bolt that goes through the entire assembly that captures both shocks. So this is that really long bolt. I think this was like a 9-inch long bolt, which it just did not look like it was strong enough to my eye. And I don't like the idea of both shocks riding on one bolt, because if that one bolt fails, you lose all of your suspension. So what I'm going to do instead is make this part a V shape rather than a flat shape. And the advantage there is that it will allow me to have separate pieces of hardware for the shock bolts, and it will drop that bottom part of the A-arm at that bottom of that V, which is a more traditional shape. And the reason I'm doing that rather than just pushing the shock mounts up is because you want the shock mount to be at or below the pivot point line between the bushings on the inboard side and the spherical bearing on the hub side. And so the way to do that is to add this V-shaped kick down on the A-arm. And this is a design that I've seen all over the place, and I didn't understand why it was the case until I went through this exercise, but it makes a ton of sense. And so unfortunately for me, there's no bend feature on a complicated part like this in SolidWorks. I had to just redesign this part entirely, but since it was a simple shape, it didn't take that long to rebuild it with that bent design feature that I needed. I'm also increasing the number of pins in the assembly, which I sort of did by accident, but ended up being the right move because these 3 components in the assembly are pinned together with 4 pins and 3 bolts. So it's going to be twice as strong in shear as it was previously. So I just need to make that simple V shape with the kick down, make sure all my bolt holes line up because there's a lot of them, and then copy that same process over to the big side of the A-arm. I can delete all those features. I was also worried about compromising the strength. I mean, that piece as it stood before had a ton of cutouts right in the area where you need the most strength. Whereas with this design, the bulk of the material is uninterrupted. So it's going to be really, really strong. And then I'll just have some boss features kicking up to capture the shocks. And then since this part was so complicated, I ended up just making a new one and referencing the envelope dimensions from the previous design, and it ended up looking a lot better. It was a lot faster than redesigning it from scratch, and I ended up with all the right clearances where I needed them. So for these shock mounts, what I do is I use one sketch to make the main boss, which you can see here. So the clearance hole and the exterior dimensions of that boss. And then I do a mid-plane extrude. And then using that same sketch, I can do a cut feature on that same plane. So I ended up with 4 bosses here without having to make 4 separate planes. I only had to make 2 reference planes and then share sketches across multiple features, which is kind of a cool trick that you can do in SolidWorks. Now I'm just cleaning up some hardware in here, and this lower control arm assembly is looking good. So I didn't go through the whole process of doing design for machining on this yet. I want to beautify this part a little bit because it's going to be really prominent on the front of the vehicle, and I want it to look as cool as possible, especially since I'm using billet. I don't want it to look like a big boxy thing. I want it to look stylized in a certain sense and cut away all those sharp corners for the purpose of strength and make it look like more of a piece of billet art than just a functional placeholder like it looks right now. So now I just need to drop some hardware in and we're looking good. So the next thing I need to figure out is how long those shocks need to be to accommodate that 30 inches of wheel travel. They're not going to be 30-inch long shocks since the shocks are mounted about halfway up the A-arm, but I still need to go through the exercise of sketching everything out to figure out where the mounting points are going to be at the top of the vehicle. So I'm taking some shock assemblies from the previous design, saving them as a copy in a new folder, and then I'm going to modify those lengths once I have them. So the way I do this is at full compression, the shock should be perpendicular to the A-arm, and then at full droop, it can be whatever angle. But what that does is it gives you a progressive shock rate. So as the wheel moves further and further up in travel, the spring rate gets closer and closer to linear and therefore increases in spring strength. And then by making those two sketches that represent the shock at droop and the shock at compression equal length, I can figure out how long they need to be and where the mounting locations need to be inboard. And I think I ended up with 18 inches of stroke on these shocks, which is totally feasible, something you can buy off the shelf from King, whereas the ones on the back were pretty crazy long. That would be something totally custom. So modifying the length, I need to modify those bypass tubes. If you remember from the last video, I used a swept feature here. So it's a circle that represents the tube and then a path on a line on an orthogonal plane. And then you can tie those two sketches together with a feature called swept boss, and the circle follows that path. It's pretty cool. If anyone's interested in longer form, non 10x time-lapse tutorials where you can actually see what I'm doing in real time, let me know. That's something I would be happy to share with you guys if you're interested. So I just dropped that coil carrier in, and the process that I like to follow here is the top spherical bearing in the assembly is fixed with respect to the vehicle, meaning it's mated to the upper assembly, and then the other components like the top of the shock and the bottom of the shock are mated to that and are allowed to move independently. And so that's how I get this really cool cycling travel in SolidWorks, by setting up those mates correctly so that one side is fixed and the other side is moving and nothing ever breaks. So the next thing I need to figure out is where the bump stops are going to live on the front of the vehicle. I think I am going to use a slapper arm design again, but there's a lot of stuff jammed in here in the front, so I need to be really careful about where I place these. Luckily, I had left myself enough room on that front portion of the A-arm, the skinny portion, where there was plenty of space for bump stop to live without interfering with the steering or the axles or the rest of the suspension components. So I'm just going to set up some limit mates here. So I have a limit mate on the angle of the A-arm, and then I have a limit mate on the distance of the bump stop with respect to its own housing. And then I just need to figure out how to mount that slapper arm in there. So I'm copying over the slapper arm from the previous Ultra 4 design, but I'm going to rebuild this part because it has that little kick down at the bottom. The reason I did that on the last design was so that I could accommodate the requirement of keeping the A-arm one flat piece of billet. But for this one, since it has a kick down and it's mounting to a smaller piece of billet, I don't need to worry about trying to conserve material stock size. I'm just going to do what's best for the design and then make the appropriate features to interface with everything. So I made the slapper arm a lot simpler, and I made the A-arm a little bit more complicated, but in a way where it's not going to make it crazy expensive. And the main thing I'm doing on this one is just reducing the length, because the slapper arm's mounted in a slightly different location than the previous design, and there's a little bit less clearance, so the slapper arm's going to be a little bit shorter to be more compact in the assembly. So I'm just making some reference sketches for the boss that's going to grab the slapper arm, and then just those two simple ears that are sticking out that everything's going to bolt to. What I ended up realizing was that this part of the design would work a little bit better if those were angled slightly. So that's what I ended up doing in the long run. And I'm adding a bearing bronze sleeve bearing or sleeve bushing in here because there's no rod ends. Since this arm only moves up and down, it doesn't pivot spherically, but it still needs a bearing surface, so it's not just steel on steel. So the bearing bronze is a good application for this so that it will move. These are internally lubricated, so I don't need to add actual bearings or a bunch of bearing housings. I can just use that bronze bushing and it'll allow the two parts to move with respect to each other really smoothly. So now I need to angle that boss slightly, and the features ended up looking really weird because they were on a strange plane and the direction of the boss extrude was not matching the plane, so I needed to do a little bit of cleanup work here on those sketches to make sure it didn't look all goofy and wonky and lopsided like it does right now. Yeah, and those planes weren't quite right, so this is something that I'll have to fix during the design for machining phase of the A-arm design. But I have this slapper arm in at a really nice angle, and so it's going to cycle smoothly, and the bump stop's going to land on the right spot on the arm where there's lots of meat of material and lots of strength. And there's still enough clearance on the tall knuckle if I just reduce the length of the slapper arm, and it's all cycling properly and it's looking great. So the front suspension is almost done. All we need to do next is the upper control arm. So the last part of the design for the front suspension that I need to do is the upper control arm, and I'm going to go with a traditional J arm on this one. So that means the inboard rod ends are mounted in front of the pivot point on the tall knuckle, and the part takes the shape of a J. On the previous design, I had kept the rod ends on the same angle pointed towards the spherical bearing, but what I realized after the fact was that disallowed me from adjusting the camber, and the reason to orient the rod ends perpendicular to the spherical bearing is that you can adjust those threads in and out to adjust camber. But the sacrifice that you make there is you have a phenomenon called rod ends in bending, meaning that the direction of the load is at a slight angle with respect to the threads of the rod end. So it reduces strength a little bit for the purpose of adjustability. Now, on the Ultra 4 design, I wanted it to be as bomb-proof as possible. And since that was designed for a low grip environment at moderate speeds, camber adjustment was not at the top of mind. It was just strength. But for this design, since it's going on a trophy truck, it's going to be going really, really fast, and camber adjustment is critical for handling. And there's just, the reality is with the tall knuckle design, there's not a ton of loads on this upper control arm. That moment arm is spread out so far that any force imparted on the wheel gets reduced by this gigantic moment arm afforded to you by the tall knuckle. And those rod ends are also enormous, the biggest ones I could find. So I'm really not worried about building everything to be the strongest it could possibly be. I'm interested in building it to be as strong as it can be without sacrificing adjustability for handling. So you can see the part starting to take that J shape here, and I'm just going to have some little cutouts to clamp those rod ends, and this is a pretty common practice for a part like this. Now, the one design compromise that I made on this that I ended up walking back was this was going to be a single shear mount, meaning that the part was going to bolt to the tall knuckle only on one side in a single shear configuration. I just don't think that's the right move. What I ended up doing was adding a support piece on the back so that it could be properly double sheared and extra strong.